Welcome to Emission Engineering, your service partner for combustion technology. Today we want to talk about the topic of fuel-air ratio control. The fuel-air ratio is one of the most important things to ensure during combustion. If the ratio deviates too much towards the air, then too much excess air is burned. This is uneconomical, usually leads to higher NOx emissions and shifts the heat transfer from the radiant to the convection part of the furnace. If the fuel-air ratio to fuel is heavy, it can lead to safety problems, such as flame instability and even flame stalling, increased carbon monoxide emissions due to lack of air, flooding, afterburning, etc. First, let's take a quick look at the theory of combustion engineering. In crude oil refineries, you will usually find fuel gas compositions that consist of gas mixtures with high methane, ethane, propane, butane, but also hydrogen. To simplify or clarify the matter, let's first compare three quite different gases: hydrogen, methane, and propane. If we look at the stoichiometry of the combustion of these substances with air, we can see that about 2.5 molecules of air are needed for complete combustion per molecule of hydrogen. The minimum quantity for conversion is also called the minimum air demand. The air number lambda in stoichiometric combustion is then 1 and is identical to the minimum air needed for combustion. For simplicity's sake, we've adopted air as a mixture of nitrogen and oxygen in a 4:1 ratio. On a closer look, the ratio is not 4:1, but rather 79.1 to 20.9. Therefore, the stoichiometric factors are divided by 0.209. This results in the minimum air demand, which is the amount of air theoretically required for the combustion of a substance. For hydrogen, this is 2.39 standard cubic meters of air, for methane 9.56 and for propane 23.92. The minimum air demand is a pure substance value and depends only on the fuel, or in case of gas mixtures, on its composition. The air-fuel ratio, on the other hand, describes the actual amount of air supplied in relation to the fuel. So it is dependent from the process and depends on how combustion is taking place. In the special case of stoichiometric combustion, both quantities are of equal size. Real furnaces, however, are usually operated with excess air. Literature refers sometimes also to a fuel-air ratio. This is simply the reciprocal value of the air-fuel ratio. This slide lists other fuels that are often found in the fuel gas of oil refineries. It is striking that the lower calorific value for most hydrocarbons hardly fluctuates in the unit kilojoules per kilogram, while in the unit kilojoules per standard cubic meter, this increases sharply with the number of carbon atoms. It is noteworthy that the minimum air demand in relation to the lower heating value hardly changes for hydrocarbons. As a rule of thumb, about 950 standard cubic meters of air are required for stoichiometric combustion per megawatt of heat released. We can later make use of this property to regulate the air-fuel ratio in a combustion system. Other gases such as carbon monoxide, hydrogen, or hydrogen sulfide deviate more strongly from this value, but these are not hydrocarbon compounds either. Let's keep in mind that density, calorific value, minimum air demand, etc. are purely physical properties of gases that do not change. Before we talk about the regulation of the air, a few words about the measurement of the amount of fuel gas. These are often determined by means of a measuring orifice. The physical measured value of such a measurement is the pressure drop before and after the orifice as a measure of the flow. In the example, let's assume that the calculation of the orifice for natural gas would have been carried out with a pressure loss of 50 millibar at 1,200 operating cubic meters. During operation, this orifice causes a flow of 300 operating cubic meters with a pressure loss of 25 millibar, which would correspond to half of the calculated total pressure loss. So the output signal of the transmitter would be 12 milliamps, and since the measurement range is calibrated from 0 to 1200 operating cubic meters, the value displayed in the process control system would be 300 operating cubic meters. 300 and not 600, because the pressure loss and the quantity are in quadratic relationship. At half the measuring range, the flow is a quarter of the measuring range. Then you carry out pressure and temperature compensation, and in the example you get 499 now standard and no longer operating cubic meters per hour of heating gas. density correction is not absolutely necessary here, as the density of natural gas is virtually constant. With the lower calorific value, the heat release in the example is calculated to be 4.97 megawatts. When using fuel gas with a different composition such as natural gas, the matter becomes somewhat more complicated. Let's assume we have a fuel gas with 50% methane and 50% hydrogen. We assume that this mixture causes the same pressure loss of 25 bar as in the previous slide. Here, too, this pressure loss of 300 operating cubic meters of gas flow would be caused, but now by a gas of a different composition than before. After compensation, this would also result in a flow rate of 499 standard cubic meters per hour. Without knowing the composition of the new gas, the DCS would now formally show a value of 4.97 megawatts. However, it lacks information about the current calorific value, because it is now much smaller. But the system doesn't know that. In the case of 50% hydrogen and 50% methane, the real heat release would be about 35% lower, namely only 3.23 megawatts, and correspondingly 35% less air would be needed for combustion. The example shows that in the case of fuel gas with fluctuating composition, it is important to record the property of the gas. The most commonly used property is gas density. But you can also use others. Without any size, adequate fuel-air ratio control is hardly or not possible. Now let's look at how the fuel-air ratio can be adjusted in practice. To do this, we start with a natural draft burner and then move on to more complex systems with several forced draft burners. As already mentioned, in the simplest case, the amount of fuel gas in cubic meters per hour is measured indirectly via the pressure difference via an orifice, and then flow gets pressure and temperature compensated. If the heating gas is a gas of quasi-constant composition, such as natural gas, the quantity can be multiplied by a constant density and the amount of fuel gas in standard cubic meters per hour is obtained. With a natural draft burner, there is no direct airflow measurement, so the fuel-air ratio can ideally be measured indirectly by measuring the excess oxygen in the flue gas. I say ideally, because in practice the oxygen content in the flue gas can be influenced by so-called tramp air. Process furnaces operate in negative pressure and are usually not gas-tight to the environment. Therefore, air can be sucked in, which is then also measured and can falsify the oxygen measurement. To minimize this, the vacuum in the firebox should be kept as low as possible. You can see more details about this in our video on tramp air and draft control on our website. In the event of load changes, it is therefore the plant operator who adjusts the oxygen content in the flue gas by adjusting the burner air damper. At 10% air excess, the oxygen content in the flue gas is about 2% by volume, at 15% air excess about 3%. With furnaces with multiple burners, there is another difficulty. Adjusting the burner air dampers so that each burner receives the same amount of air is difficult in practice without additional aids. This is where the furnace optimization tool, even patented by us, can help. With this, the airflow can be measured and adjusted indirectly via the pressure loss on the air side via the burner. The best way to learn about this is to watch our video on our website. In rarer cases, there is an automatic airflow control for a common air damper of several burners, whereby an individual air setting for each burner is then again manually made by the plant operator with even. Now let's look at furnaces with forced draft burners. First of all, the case of a single burner per furnace operated with natural gas. The fuel skid arrangement is usually identical to that of natural draft burners. But the difference now arises in the air supply, which is usually done via a blower or air fan. Let us first assume that the airflow is recorded in operating cubic meters per hour via a venturi flow meter. Then a correction for the air temperature is usually sufficient to determine the airflow in standard cubic meters per hour. The 9.6 is multiplied by 1.15 by the minimum air requirement of 9.6 standard cubic meters of air per standard cubic meter of natural gas and a residual oxygen content in the flue gas targeted by the process control system, in the example 15% or 3% by volume of oxygen. The ratio to be set is therefore about 11 standard cubic meters of air for 1 standard cubic meter of natural gas. the airflow measured by the venturi measurement is compared to this. If the actual supplied value is smaller, then the air inlet damper of the blower opens, or if the value is greater, it closes slightly. As an alternative to an inlet damper, a blower can also be used with a variable frequency drive. If the measurements for the fuel gas and air volume were 100% accurate, then the oxygen content in the flue gas would be exactly 3% oxygen by volume. To understand the difference between oxygen control and fuel-air ratio control, it would not be necessary to measure the oxygen content in the flue gas with a pure fuel-air ratio control. This is important to understand, because there are refineries who speak of or think they have a fuel-to-air ratio control, but in reality, it may be formally designed, but practically inactive. Then it is controlled almost exclusively with the help of the oxygen probe. But this is then formally an oxygen and not a fuel-air ratio regulation. In the case of a fired heater with several forced draft burners, the same procedure must be used as for a furnace with only one burner. The only difference is that the air is distributed unevenly among the burners, as is the case with burners with natural draft operation. As a rule, this is even more serious with forced air, which is why our system for optimizing air distribution even is particularly suitable there. Let us now come to the more relevant case in practice, that the fuel used is not natural gas, but a fuel gas whose composition varies greatly, which is common in refineries. Assume that the fuel gas fluctuates with a density of 0.5 to 1.5 kilograms per standard cubic meter, a quite realistic range. If there is no measurement of any fuel gas properties, such as density, calorific value, WOB index, or others, control becomes difficult due to a lack of input information. So you can't use the fuel-air ratio control to calculate and then adjust the amount of air that would be necessary to obtain a certain oxygen content in the flue gas. In these cases, the tendency of refineries is to automatically manipulate the values of the minimum air demand or the fuel-to-air ratio in the process control system from the oxygen content in the flue gas in such a way that the desired oxygen content in the flue gas is achieved. Let us remember that the amount of air that is necessary to burn a certain amount of fuel gas is exclusively a function of its composition and should not be manipulated by a sensor, in this case the oxygen probe, which has a manipulating influence to get the desired results. It is literally a fake control. If you select the manipulation area simply large enough, any fuel gas can be burned. At first glance, the control scheme has a fuel-air ratio control, but only at first glance. At second glance, you can see that it is the oxygen measurement that is constantly regulating. In such cases, we recommend that you always mark the graphic in the process control system in such a way that the currently dominant control path is visible. This makes it easy to see that the control takes place via oxygen and not via the ratio control. Even if the oxygen control system theoretically works temptingly well, this has safety pitfalls. Oxygen sensors, such as those made of zirconium dioxide, can be subject to measurement drift, which requires their periodic calibration. Incorrect measurements, especially in the case of a larger supply of tramp air, heavy rainfall events, etc., can have a massive influence on the measurement, without an oxygen control system causing appropriate settings of the combustion air. In this slide, we assume a fuel gas consisting of the components hydrogen, methane, and propane. The composition that is common in your company should be clarified in advance as part of a fuel gas composition study. As many laboratory values as possible for the different components of the fuel gas from the past should be examined. Select them according to the following criteria. If there are no significant inert gases, such as nitrogen, CO2 or similar, look for the composition with the lowest and highest heating gas density. In addition, a composition that represents a kind of mean or typical composition. To at least consider natural gas as an alternative fuel is usually very helpful and often also relevant in practice. If the inert gas content in the heating gas is greater than 10% by volume, look for the extremes in the WOB index instead of the fuel gas densities. If you always use such compositions whose sum of all components result in 100% by volume, you do not specify ranges of 25 to 65% by volume, as can be seen here, for example, methane, because this cannot be calculated exactly. You can put together almost any number of combinations with such areas, but this makes it difficult to receive emission guarantees from a furnace supplier, and that is bad for the refinery. If, for example, when planning a new plant, you need emission guarantees for your furnace, then you should send all laboratory values to the potential suppliers in this form. You should sort out compositions that seem atypical or faulty beforehand, because it can happen with laboratory values that errors occur. Basing emission guarantees on inconclusive laboratory values may lead to a completely different design of the furnace and can make projects unrealistic or uneconomical. As a rule, refinery fuel gases do not have critical components that can easily lead to emissions not being met. Critical could be the following: ammonia, amines, or other nitrogenous compounds in relation to NOx and sulfur-containing components due to SOx emission guarantees, possible dew point undershooting and associated corrosion in the flue gas path. Specifying realistic fuel gas compositions in the full range is essential for the design and subsequent operation of the plant. From the compositions determined in the study, a correlation is created between the calorific value in kilojoules per standard cubic meter and the fuel gas density in kilograms per standard cubic meter. Here is an example of the correlation between the gases hydrogen, methane, and propane considered. A similar correlation can be found in which the minimum air demand in standard cubic meters of air per standard cubic meter of heating gas is plotted over the fuel gas density. Both correlations are then stored as a function in the process control system. Alternatively, you can also create a correlation between fuel gas density and minimum air demand per megawatt. This is an elegant variant because, as we have already seen, the value of the minimum air requirement in terms of megawatts is almost the same for most hydrocarbons found in refinery gas. The correlation between the calorific value and the fuel gas density is used to determine the rated heat output by multiplying the amount of fuel gas by the lower calorific value. You can see here again that you would theoretically not need an O2 measurement in the flue gas with this ratio control. However, field measurements are always more or less error-prone. In addition, problems with the speed or accuracy of a measurement can also occur in practice. If, for example, a fuel gas composition changes significantly within a few minutes, for example the density from 0.5 to 1.2 kg per standard cubic meter, then the density measurement of the fuel gas may not be able to detect these changes quickly or accurately enough. Especially if the fuel gas changes to higher densities, it can then quickly lead to a lack of air. In this case, the presence of oxygen measurement in the flue gas is important, because it can usually detect this and intervene in a regulating manner. In this case, it is okay and also wanted that the fuel-air ratio control no longer acts and the oxygen control takes over. As soon as the fluctuations in the fuel gas composition have subsided, the ratio control should then take over again. This slide is identical to the previous one, with the exception of the fuel gas fluctuation range. It is smaller here and can be realistically found in refineries. The basis for calculating the correlations is then better adapted than in the previously considered system of hydrogen, methane, and propane. Better than a simple density measurement would be a so-called WOB analyzer in the fuel gas line. This usually determines not only the lower calorific value, the minimum air demand, the heating gas density, but also the WOB index. The lower calorific value is used directly to determine the heat release. The minimum air demand is fed directly into the control loop, for example without correlation as in the previous example. Fuel gas density and/or WOB index can be used, for example, to generate an alarm that allows the plant operator to take the fuel gas control valve on hand at the process control system in order to absorb any fuel gas fluctuations. During the planning or after the construction of the plant, the measurement principles used in the individual measurements must also be taken into account. If you use an orifice or vortex measurement for fuel gas flow, then the laboratory should output calorific value in kilojoules per standard cubic meter. For Coriolis and hot wire anemometry in kilojoules per kilogram. Therefore, if possible, avoid the conversion via the gas density, as this may involve additional measurement errors. Basically, all field measurements have certain measurement errors. Experience has shown that these are lower for mass-based measurements than for volume-based measurements. However, they are usually more expensive and more vulnerable. In case of doubts about the measurement of the air volume, one should be able to carry out a comparative measurement. If, for example, you have a venturi measurement for the air, you should provide a minimum of 2 small holes at a flow-count point of the air duct, through which you can carry out a comparative measurement with a pitot measuring tube, for example in the form of a network measurement, and thus compare both measuring principles with each other. If there are deviations, a corresponding factor can be adjusted in the process control system so that the measurement is correct again. In practice, this is unfortunately rarely, if ever, done. This can lead to the measured quantities of air and fuel gas being driven in a ratio displayed in the process control system that does not correspond at all to the stoichiometric conditions. A simple estimate can already provide information here. To do this, let's look at this example. Suppose you burn a natural gas quantity of 1000 standard cubic meters per hour, that is about 10 megawatts. As we know already, stoichiometric combustion requires 9.6 standard cubic meters of air per standard cubic meters of natural gas. If you have given a set point for the excess oxygen of 3% by volume, then you get the excess air of about 15% or a lambda value of 1.15 with this formula. If you multiply these, you know that you need about 11,040 standard cubic meters of combustion air. But if my venturi currently measures only 9,500 standard cubic meters per hour, as can be seen here, you know that something must be wrong. Physics does not lie. So, there must be a measurement error. The estimation works in a similar way with the help of the heat release. Of course, the fuel gas measurement can be faulty. The same can apply to the airflow or both measurements. In this case, one would first check all formalities. These are checking the data sheets for the measuring orifice and the venturi. Was the calculation done correctly? Are the pressure differential transmitters calibrated to the correct range? Are the connections tight and professionally executed? Could there be any blockages? Are the impulse lines for the measurements with a constant gradient laid? Is the signal transmission to the process control system okay? Depending on which measuring principle is used, preferences are available. If the amount of fuel gas is measured with an orifice or a vortex measurement, for example on a volumetric basis, then the laboratory values for the calorific value should be in kilojoules per standard cubic meter. In methods measuring mass flow, such as Coriolis or hot wire anemometry, they use the lower calorific value in kilojoules per kilogram to calculate the rated heat output. Volumetric methods are mainly used for air volume measurement, such as the venturi, the annubar, the pitot or pitot tube or aircraft wing profiles. It is clear that measurement errors can occur in many places, so it is also important to maintain these measurements so that they provide comprehensible results. Let's summarize. We have learned that combustion processes can be calculated exactly with simple engineering. As long as you make the right assumptions, you can calculate everything formally. Trust in it. A mass balance always works, and as is well known, no mass is lost in combustion reactions. In the event of discrepancies, it must be due to measurement errors that must be detected and eliminated. Do not forget the safety aspect of such a fuel-to-air ratio control. According to DIN EN 746-2 or 13577-2, this ratio must be carried out with a SIL 3 or equivalent classification. A control system in which the minimum air demand for airflow measurement is constantly manipulated by means of the oxygen content in the exhaust gas may not meet this protection class or only incompletely. It should therefore be in your very own interest that the fuel-air ratio control works properly and that its oxygen measurement only intervenes if you move outside a desired oxygen range in the flue gas. If you have any questions or need our support, we will be happy to help you.
Emission Engineering. We engineer your emissions.